Okay, inner product spaces are special type of norm vector space. Okay. So that is essentially the circle we've done so far, right? Norm vector spaces is everything. We did this special example of step functions and L1, and now we're learning about a new type called an inner product space. That's what we're going to learn today. We're going to see the main example that we want. L1 was functions that are integrable. So L1 was functions, the L1 space of R. It was the set of functions such that the integral of the absolute value of f is less than infinity. That is the space L1. And the main example, the main important example that we're doing, and the reason we did all the work in chapter 2 to define the Lebesgue integral, is the main example we want is this space called L2, L2 of R. That's the main example that we want, and it lives in this intersection. It is both a norm vector space and an inner product space and a complete space. It's all three. It has all the nice properties that you would want. And this space L2 of R is very similar to L1 of R. It's the set of all functions f. Does anyone know what the condition is? I think we very briefly discussed it in the first week class. Yeah.
It's the square root of the integral squared.
The norm, yeah, this is very good. So the norm in L2 is the square root of the integral squared. So you do the integral squared. So you take the absolute value of f squared, and then you take the square root at the end. And it's important you take the square root at the end because norms are supposed to be homogeneous with respect to constants. So if you multiply f by 3, then you would multiply f squared by 9, and then we want to multiply the whole norm by 3, so we're going to take a square root at the end. That's why we put the square root there. But the condition is exactly what you would read from this, is that the integral of the square of the function has to be finite. So L1 is the space where the integral is finite, and L2 is the space where the integral squared is finite. And that makes them very slightly different spaces. We'll talk a little bit about that in between. But the main reason we want to do this is L2 is a really beautiful space. It has all sorts of really beautiful properties that the other things don't have. And it's both an inner product space and a complete space. That's the reason we're doing this. And this is where we're going to do Fourier series. So Fourier series are living in this L2 space, or at least the most basic version of Fourier series. Not Fourier space, Fourier series. Okay. Oh no, my circle has been robbed of me. Okay. Fourier series. Series spelled wrong. Okay, that's fine. Okay. That's what we're going to do. This is kind of a big picture. By the way, this overlap between inner product spaces and complete spaces also has a name. So there is a name given to spaces that are both an inner product space and complete. It's not just a Banach space. Does anyone have a guess what that is? Yeah. It's a Hilbert space. So this is the title of the book that we're using is Hilbert spaces, and Hilbert spaces are things in this overlap. Let's see, how do I do it? I guess I'll write it in blue. Hilbert space. Hilbert space. Hilbert space. So Hilbert spaces are the things that are both inner product spaces and complete. And that makes them a special type of norm vector space, a special type of Banach space. And here is a quick little, let me copy paste in a quick little quote from the textbook. This is right at the top of the introduction to the chapter. So this guy is a famous French mathematician. He says, Hilbert spaces constitute at present the most important example of Banach spaces, not only because they are the most natural and the closest generalization in the realm of infinite dimensions of our classical Euclidean geometry, but chiefly for the fact that they have been up until now the most useful spaces in this application to functional analysis. So almost all the time, if you're going to use something in real life, quote real life, then you will use a Hilbert space rather than a general Banach space. And a good example is quantum mechanics is all about Hilbert spaces. Quantum mechanics is all Hilbert spaces. So that's why we're doing what we're doing here. Okay. That's the big picture. Another example, let's do another example. PDEs. PDEs have a ton of this stuff where you define certain spaces where the things do what you want them to do. I'm trying to think of other examples, but let's leave it at those two. Okay, so that's the big picture. Now we're going to jump in. The next thing I'm going to tell you is the definition of an inner product and what is an inner product space, and then we're going to start going from there. But this is a good place for any big picture questions. Okay, let's see the definition of an inner product, and I will copy and paste it from the notes so that we match their notation exactly, and then I will discuss all of them. Okay, so this is the most important definition, I guess, for this type of thing. So an inner product space is a space that has a thing called an inner product on it. Mathematicians are very creative with their names. Thing with an inner product is an inner product space. We use this notation for an inner product, which is these two angle brackets. So the angle brackets look like this. And the angle brackets, they put two dots. They're saying it inputs two vectors from the space E, and it must satisfy these conditions. Before we tell you the conditions, let me give you the best example so you can have it in your mind. An example, which is the ordinary space, okay. Ordinary space, let's say ordinary Euclidean space are, I could say to the end, but let's just keep things concrete and say R4. So in R4, it's the set of all vectors of the form x1, x2, x3, x4. This is just like you learned about in linear algebra class. X's are in R. Okay. So, and then the inner product on this space is the inner product of x and y is defined to be the sum x1, y1 plus x2, y2 plus x3, y3 plus x4, y4. So everything we're doing is really, like this came from geometry, like the ancient Greeks knew about this, and we are generalizing it. We're saying, what properties should this bracket thing have to make it make sense for an infinite dimensional space, to make it make sense for a set of functions? What kinds of things would we want to have? This is a good point in time. Who has seen like a linear algebra class where they talked about this kind of thing? Okay, almost everyone. This will help you quite a lot. Unfortunately, if you haven't seen this, I know linear algebra is not technically a prerequisite. You'll have to just like learn the abstract definitions without having the concrete thing to think about. But this is super helpful to think about. One thing in particular is if you have an inner product, the inner product is related to the norm. So if you have in regular Euclidean space, there's a formula for the norm of x in terms of the inner product. Does anyone remember that formula? Yeah.
I believe the norm of x is the square root of the inner product of x with itself.
That's exactly right. So if you do the inner product of x with itself, that would be not x, the norm of x, that would be the norm of x squared. So you could put the square root on the other side, but I'm going to write it like this with the norm of x squared. And so this is how you get the norm. The textbook, for whatever reason, does not want to tell you the definition of the norm until way later. So until I think it's even, is it in a different section? Okay, no, it's not. Okay, it is in a different section, 3.2.11. It's way down here. But when you have an inner product, you automatically get a norm, and the norm is defined exactly like this. So the formula for the norm in terms of the inner product is the same whether or not you're in the ordinary Euclidean space or in whatever weirdo inner product space you're in. And that's why inner product spaces are a special type of norm spaces. There are places where you have this inner product, and the inner product gives you a norm by this formula. Okay. What does the inner product have to satisfy? What is the inner product? Well, it has to satisfy these properties. One is that the inner product of xy has to be related to the inner product of y and x. When they're complex numbers, so if the inner product is complex, then they are not equal, they are equal up to complex conjugate. In this course, we're almost always going to do real inner products. So for real inner products, real valued inner products. So in some situations, it really is more convenient to do complex valued ones, but for the most part, we're almost always going to do real ones. And for real ones, it just says xy equals yx. Xy equals yx. That's what the thing says. So you switch the order, the inner product of x and y is the same as the inner product of y and x. That's condition A. Condition B says that inner products are linear with respect to vector addition in the first component. So with one component fixed, this is linear. Linear in first component, let's say linear in first component. When second component second component is fixed. Okay, so that's very important. You have to have the same z everywhere in the second component to make it work. The third thing says the inner product of x with itself has to be greater than or equal to 0. This one is important because otherwise it would not define a norm. So this must be true, must be true, must be true, or else. Norm wouldn't work, right? So when you go to take the square root in this definition, the thing you're taking the square root of better be a positive number. That is what it is saying. And lastly, this condition that the norm of x with itself equals 0 implies x equals 0. That was a condition from the norm vector space already. So this is kind of C and D are both making sure that this is a legitimate norm vector space when you define the norm in the way that you think. That's the definition. This is very simple. It really does all the things that you would expect it to do based on your experiences with this example from R4. So the only thing that will be different is that we're going to work on infinite dimensional spaces, and then we're going to have all the infinite dimensional weirdness, but the actual rules of the inner product are exactly the same as this. Okay, questions or comments about that? Okay, let's see some examples. So we did one example. This is the most boring example. The simplest, interesting, infinite dimensional example, an infinite dimensional example. And this is related to what we were doing way back in chapter 1, is the sequence space. So a sequence space. And I'm going to write them like this. I'm going to write the set of all x of their sequence is x, such that xi is a sequence. And I'll write it like this with brackets, I going from 1 to infinity. So every element of the space is itself a sequence. The reason this kind of twists your mind sometimes is because very often in this course we have sequences of things from the space, and then if the thing is a sequence space, then you have a sequence of sequences, which can be hard to get your head around, but this is the kind of stuff we were doing in chapter 1. And the space I'm going to look at is called little L2, And little L2 is the set of all sequences, so the set of all xi, I going from 1 to infinity, such that you need a condition, and the condition is that the sum of the squares of the x's are finite. So you not only can you sum up the sequence, you can square all the entries and still sum it up, and that will be fine. And let's make it real valued. To keep things simple. You could also do the complex value. If you do the complex value, you wouldn't do the sum of the squares, you do the sum of the absolute value squared. But let's just live in real land for now. And the inner product on this space, so the inner product of two sequences A and B, is the sum from I equals 1 to infinity. It's again an infinite sum. Can anyone guess what would the formula be for the inner product? Yeah.
A of I times B of I.
It's A of I times B of I, right? So you multiply them together. It looks very similar to what we did in R4. In R4, there were 4 components. In little L2, there's infinitely many components, but you multiply them together entry-wise, and then you add them all up, and that sum will be finite. You might ask, okay, here I did AI times BI. I said the AIs individually squared are finite, the BIs individually squared are finite, but could it be that the sum of the squares of the AI is less than infinity, the sum of the squares of the BI is less than infinity, but if you do the sum of AI times BI, it's equal to infinity? Is this guaranteed to be a finite number? Yeah.
I think so, because you can guarantee that one of them is greater than the other.
That's very good, yes. So it turns out there's an inequality. We're going to learn this inequality in a few minutes called the Cauchy-Schwarz inequality, by the Cauchy-Schwarz inequality. And we will do this momentarily. I believe nowadays there's a third person I'm supposed to attribute to in addition to Cauchy and Schwarz, but I don't remember their name, so I guess I'm a horrible person. In the textbook, they only have Schwarz. They left Cauchy off, which, okay. By the Cauchy-Schwarz inequality, if you Google the Cauchy-Schwarz inequality, you will know. The inner product of A and B is less than the norm of A times the norm of B, as long as you square it. So if the sum of the A's is finite and the sum of the B's is finite, the sum of AI times BI will also be finite. That'll be some actual number. Do note that it could be positive or negative, right? AI times BI can be positive or negative, even though the entries squared are positive. So the norm is always positive, but the inner product can be positive or negative, and that can happen. Okay, this is the most basic, interesting example. We're going to do this inequality in a second. The most useful, interesting example is not little L2, but capital L2. So this is the most useful example. And this is like the function space that everyone will know and use for most things in math. And it's the space L2 of R. And that's the set of functions such that the integral of f squared is finite. Okay? And the inner product on this space is probably what you can guess what it will be. The inner product of f and g. What should it be? F times g. Okay, someone said it. Okay, very good. So you multiply f times g and then you integrate. You should think of integrating, this is equal to, okay, if you were writing it in the ordinary notation, it would be f of x times g of x dx. And this is equal in quotes. Don't tell me, integration is kind of like a sum of x, right? So this is kind of like the things we were doing before, right? The reason you multiply them and integrate is you're taking them entry-wise and you're comparing them and then kind of averaging that over your entire space. Of course, we know by now the integral is a lot more complicated than the sum. But we know how to handle an integral. And it's really important that we proved all the properties of the Lebesgue integral so that we will have the properties for L2. So in fact, all those properties we did in chapter 2, the reason was we're going to now use them to prove things about L2. And one thing in particular, our goal, I don't actually know if we're going to get to this goal or not. We will see. Our goal is we will prove Fourier series converge in L2. Fourier series converge in L2. And specifically, this says something like the function f is equal to the infinite sum from n equals 1 to infinity. And you put in coefficients alpha n, and then you put in the function sine of nx. And this will be true. Okay, you need a separate one with some different coefficients for cosine of nx. So in other words, it's possible to write every function in L2. If f is in L2, you can write the function as an infinite sum of sines and cosines. Let me also not say in L2 of R. Let me say in L2. It's going to be in L2 of minus pi to pi. That's important. Let's do it like that. So if you have a function which is in L2 from minus pi to pi, then you can write your function as an infinite sum of sines and cosines. And these limits mean limits in L2, right? So with respect to the L2 norm, the L2 norm is this norm that we talked about over here of the integral squared, right? So that's like the most useful thing that can come out of this stuff is Fourier series, which is used all the time. Every time you download an MP3 or open a JPEG, you are using Fourier series. This is like the cornerstone of a lot of modern mathematics and thinking is this stuff. Okay, that's what we want to get to. That's why we're doing inner product spaces. Okay, this is a good place for questions or comments. I think the next thing I'm going to prove is the Cauchy-Schwarz inequality, but was there another example? Oh, yeah, okay. I think I'm going to do the Cauchy-Schwarz inequality next. Questions or comments? Okay, let's do the Cauchy-Schwarz inequality. This is the most useful inequality on an inner product space. And in the textbook, they call it theorem 3.2.9. You see they left off Cauchy. While you're copying it down, let me look up who's the third person because I feel bad. Cauchy-Schwarz. Again, this person was not attributed when I was a student. Am I thinking of something else? Oh, yes. Okay. It's a Cauchy-Buyankovsky-Schwarz inequality. So don't forget Buyankovsky. They are also attributed, right? It's like they all came up with this idea around the same time. So who do we name it after? I think Cauchy has enough stuff named after them. I think we should just drop Cauchy. They'll be okay. They have Cauchy sequences. They're already in there. That's good. All right. So what does the inequality say? It's just that if you do the inner product, that's less than doing the product of the norms. Did I write it with a square before? If I wrote it with a square before, that was wrong. When I wrote it up here, that was wrong. Okay, good. Let's, okay. This should not be there. Okay, yeah, so the inner product always has sort of the units. If you think of x as a vector, the norm of x has the units of length, right, the length of x, and the inner product has the units of length squared. So this is like a length squared compared to a length squared. The way I should think about it, this is like how you think about it. Think in 2 dimensions or r dimensions, remember that the inner product of x and y in absolute value, not only is it less than x times y, it's equal to x and y times some constant. X times y times some constant. Let's call the constant c. And c is less than 1. C is less than 1. This c has a nice interpretation. The inner product, this is, say, in R2 in the plane. You do the inner product of two vectors in the plane, and you can compare the inner product to the length of the two vectors. There's some constant c. C is less than 1. What is the constant c? Does anyone know? Think of your favorite thing that is less than 1. Less than or equal to 1, I guess. Yeah?
That's not 1, is it?
Well, it's not always 1. It depends on the vectors. I'll give you an example. If you do two vectors that are perpendicular, it's going to turn out that when they're perpendicular, c is equal to 0. Because the inner product, like think of this one. This one has an x component and no y component. This one has a y component and no x component. So when you multiply them together, you get 0 plus 0, which is 0. So c is 0. If you do them and they're in the same direction, what if it's the same vector twice? If you do them like this, then you're going to get the c will be 1, right? Because you'll just multiply the x component by itself squared. That's the normal thing. Yeah?
Is it the cos of the angle?
It's the cosine of the angle. So in fact, c is the cosine of the angle. The cosine of theta times x and y. This is what you learn in like high school geometry class. Is that the cosine of the angle is the inner product. And then you learn that like fancy cosine rule for like the Pythagoras theorem and obtuse triangles and stuff. So in 2 dimensions, the inner product is the cosine of the angle times x and y. And the Cauchy-Schwarz inequality says, look, it works in general. It's always less than or equal to 1. You could define in high dimensions, and in fact, people do this. For example, in neural networks, this is done a lot. You could define the angle between two vectors. You could define it by saying the cosine of theta is by definition equal to the inner product divided by the product of the lengths. And this is used in machine learning all the time. They have a vector that means cats and a vector that means dogs, and they say the angle between cats and dogs is 1 degree, and that means cats and dogs are very similar or something. So this is used all the time to make sense of high-dimensional vector spaces and to think about them geometrically. You can use the inner product to define the length, and it's all kosher because of the Cauchy-Schwarz Boolean-Kofsky inequality. Because otherwise, you wouldn't be the cosine of anything. If it was equal to 2, there's no angle that is equal to 2. Okay, that's what we're doing. Let's prove the inequality now. And the proof is a very slick trick. Here's a proof. The proof goes like this. We're going to make a function. Let me make sure I have the proof actually correct in my mind. Okay, yeah, all right. We're going to make a new function called q. It's going to be called q. Q of alpha. Q of alpha. It's some new function. And you will rightly ask me, who the hell came up with q of alpha? It was Boolean-Kofsky. Okay, q of alpha is equal to x plus alpha y inner product with x plus alpha y. So when alpha equals 0, it's just x with itself. When alpha equals 1, it's x plus y with inner product with x plus y. It's some function that depends on alpha. I don't know why we did it. I guess we'll find out in a second. But here's the thing, we can expand it. We can expand it. And the reason we can expand it is because inner products, they behave like multiplying in brackets. This is called being a quadratic form. So this is a quadratic form. Quadratic form. And quadratic forms mean you can expand it out. I'll write out what the expansion is and then I'll talk about it. It really is just like FOIL when you're in grade 5, right? First, outside, inside, last, right? First with first, x times x. First with outside, x and y. Inside, outside, inside. I don't actually know how FOIL works. Okay, I know how this works. I don't know FOIL. But if you do the inside-outside thing, what will you get? You'll get x with x plus alpha y with x plus x with alpha y plus alpha y with alpha y. Okay, and why is this okay? Like, how? I'm just saying you can do it. What is it? How can we be sure? Like, what would be the proof? What would you write down to convince somebody you can do it? Yeah.
Well, you could write like you could let one of them be equal to like z, and then you can just do scale, like you can do the properties of scale.
Yes, exactly. So in other words, what I've done here is I've actually skipped like 2 or 3 little steps, and the 2 or 3 little steps are use the properties of the inner product. So remember, If you call x plus alpha y, you call that z, and then you go back up to our definition. The inner product must satisfy all these funny definitions. Like, for example, B says you can expand out the first component. If you first expand out the first component, and then you switch which one is Z with A, and then you like expand out you do a bunch of these steps, and I promise you it will work out. So these steps are sort of written in the most simple way. So why don't we add that as E? Let's add E over here, which is that it says X plus C. Let's do A, B, C, D. Okay. If you do A plus B with C plus D, this will be equal to AC plus BC plus AD plus BD. Okay, and this is actually a good exercise, is prove that condition E holds given conditions A and B. Yeah, you only need conditions A and B. So that's an exercise for you. This is what I'm using. I'm using this expansion property, and I'm saying it follows by using A and B in the appropriate ways. That's a good exercise. So exercise, prove this. Okay. This one is the most useful. You will, in practice, you will use E all the time, and you will not really use A and B as often. E is useful. Okay, that's what I'm doing here. And I think the best way to remember is it behaves like multiplication in brackets. It follows the same rules. Now we can do one more thing. I can pull out the alphas. You can see I can pull out the alphas over here. X times x plus alpha, y times x. Okay, here's the thing. I pulled out an alpha from the first one. That's allowed. Let's go back to the rules. The rules say I can pull out an alpha from the first one. I hope that's what the rules say. Okay. I can pull out an alpha from the first one. Yeah. That's rule B, right? Put beta equals 0. I can pull out an alpha from the first one. Question. Am I allowed to pull out an alpha from the second one? I would like to pull out this alpha times y and say alpha times xy. Can I do it? Yeah.
You have to compose conjugate.
That's right. You have to. So if you were going to do it correctly, you wouldn't get alpha. You would get alpha bar. And the reason is that when you do a swap, you have to do the bar from condition A. So when you swap it, then you do condition A, and then you pull it out with by condition B, but it comes out with a bar because there was a bar of it from condition A. Again, so if you want the full proof, you should read the textbook. It's almost exactly the same, but let's do the proof only for R valued ones, so I don't have to worry about this. So let's do for R valued inner products. That will just make our life a little bit easier. And the complex one is still true. You just have to be a little bit more careful with these bars. So in general, in an inner product space, you have to worry about the bars. But for today's class, let's not worry about the bars. Okay. So I'll write should be a bar here. Should be alpha bar. But we are doing R only today, R only. And so alpha equals alpha bar. Okay, they're the same thing. And so I'm just going to write alpha. And when it's real value, you really can just pull out alpha from the second component. So you get alpha times xy. Okay, what about this last one? There's an alpha times y and an alpha times y. I want to write it as something times yy. What will the something be? So I want to pull out. Do I get alpha? What do I get? Yeah.
Alpha squared.
You get alpha squared. It is true you get alpha squared. Again, watch out because in complex land you wouldn't get alpha squared. You would get alpha times alpha bar, which would be the absolute value of alpha squared. But in real land, you get alpha squared. So I'm just gonna write alpha squared, and then I'll put the arrow here as well to remind you to watch. Okay. Very nice equation. There's one other thing you can do. In real land, yx and xy are exactly the same, so I can group these two terms together. Okay. 2 alpha xy plus alpha squared times yy. And now I can notice that xx is the norm of x squared plus 2 alpha times xy plus alpha squared times the norm of y squared. So this is my function, q of alpha. Okay. Have we gotten closer to proving the inequality? The inequality says something like the inner product of x and y is something compared to the norm of x and the norm of y. And I have this kind of equation. Why is this helpful? It turns out you can prove that this kind of equation is greater than or equal to something. Can prove Q of alpha is greater than or equal to something. Yes, it's greater than or equal to something. And if you put in that something, then this will be an equation that says the norm of x and all this stuff is greater than something, and I can rearrange it to get that thing. What is the something, and how would you prove that Q of alpha is bigger than that something? Seems very mysterious. I will give you a hint. I named it Q. Q stands for a word that you might notice. What kind of function is Q? Yeah.
Isn't it you make alpha equal to the quotient, so it'll be inner product of x times y divided by the norm of
I think you have the right kind of thing. What kind of function is Q for the other people who haven't seen?
quotient or fraction?
And it's not quotient. No, it's a different type. Yeah.
Quadratic.
It's a quadratic. Q is a quadratic. This fancy inequality is just saying quadratic equations have a minimum. Okay? If you draw a picture of Q of alpha, it looks like this. It's a dopey quadratic equation. And it's a quadratic equation that opens upwards because it's alpha squared times something positive. And it has quadratics have a minimum. Where is the minimum of a quadratic equation? It's exactly where Sala told us. It's at alpha equals minus b over 2a. Do you remember that equation from high school? It depends how hard you went on quadratics when you were in high school. I went pretty hard on quadratics in high school. This is why I know this stuff. If you want it, you can do it with calculus too. I don't know, find the minimum of a quadratic equation. And so Q of alpha will actually be larger than what happens when you plug in the minimum. And at the minimum, it's Q of, we're going to plug in minus b over 2a. Minus b is minus 2xy, right? This is the b value of the quadratic. And then divided by 2a, a is the norm of y squared. So can prove by quadratic stuff, quadratic equations theory. Oh man, what a great name for a course, quadratic equation theory. I think when I was in grade 10, the course was called Functionality, which stands for functions and relations. But quadratic equation theory would have been a way better name. Okay, we're gonna plug this in. We're gonna get the inequality. But is it clear what's going on or why it's greater than some people are nodding? Okay, good. So we're using quadratic equations, and look, we cooked up a really clever quadratic equation, right? I think this is the actual hardest part of the proof. Was the first line was cook up a quadratic equation using the inner product. Inner products have this like quadraticness to them, and that's what we're using here. Okay, so if you plug that in, you get Q of alpha is larger than this, and on the other hand, this is larger than 0. So 0 is larger than this. Okay. Let me just plug this in. Q of alpha, Q of minus 2xy over the norm of y squared equals the norm of x squared plus 2 times all this stuff, minus 2xy over the norm of y squared times xy plus all this stuff squared. Minus 2xy over the norm of y squared times the norm of y squared. Okay, and if you simplify this, this will be the norm of x squared. We got minus 4xy squared divided by the norm of y squared. Over here, we have a plus 4, and we got xy squared over the norm of y squared. So look at this crazy miracle. We have minus and a plus, and they cancel out. Let me make sure I did it right, because now I'm working.
I think your coefficients are wrong.
Which one?
So if you're doing negative b over 2a, you're missing the 2 with the y.
I forgot a 2. Okay, thank you very much. Yes, okay, very good. Let's put a 2. I knew, I was like, I don't think it's supposed to do that. Okay. Okay, so this one comes with a 2, and then this one comes with a 4 because it got squared. Okay. Thank you very much. That's exactly what we need. Okay, that looks better. Okay, so what is this? This thing should be something like this. X squared minus 2xy over the norm of y squared plus, and then plus 4 times the norm. 4 over 4 is plus 1. Okay, great. Plus 1. Okay, xy squared over the norm of y squared. And look, lo and behold, the last two terms are actually the same, except for one has a coefficient of -2, the other one has a coefficient of plus 1. Okay, so we get the norm of x squared minus xy squared over the norm of y squared. And this is the minimum value. This is like the minimum of the quadratic equation. Let's call this q star. Q star is the minimum value of the quadratic equation. Okay. If it was true that q star was greater than 0, we would be done. Okay, so let's say, suppose q star is greater than 0. Suppose q star is greater than 0. Then 0 is less than the norm of x star squared minus xy squared over the norm of y squared. And then you rearrange the equation, and it should work. Xy squared over the norm of y squared is less than or equal to x squared, and therefore xy squared is less than x squared times y squared, which is what we wanted to show with squares. So if q star was bigger than 0, we'd be done. Is q star bigger than 0? How do we know? Yeah.
Well, q was greater than or equal to 0.
That's right. That's exactly right. So the function q, the way we defined it, it's the inner product of something with itself, and that is always greater than 0 by definition. So the thing you could add to the beginning of your proof is notice q is always greater than 0. Q of alpha is always greater than 0 by the axioms of an inner product. So not only is q a quadratic equation, the axioms of an inner product say it's always greater than 0, and in particular that means it must be greater than 0 at its minimum value. So the picture I drew over here, right? I drew it above the axis. You could have also imagined a quadratic equation that goes below the axis, right? But it's always like this. Q star is bigger than 0. So Q star greater than 0, greater or equal to 0 by the axioms. And because it's bigger than 0, and because we had a formula for it, it works out to this inequality. Very beautiful proof. And I remember I saw this proof and I was like, this is a stupid proof. This is just like you do a bunch of stupid stuff and then like the stupid answer comes out. But now I see that it really is telling you that there's something very quadratic equation about inner products. Inner products are kind of like something multiplied with something else, right? Like the fact that when you multiply something by itself, it's greater than 0. That's a product of, that's what squaring things does. The fact that you can expand it out the way you expand out products. Like really the proof of this is saying, look, inner products and multiplication are kind of related in a weird, funny way, and it's got to satisfy these steps. That's how it works. Okay, that's a really important inequality. We're going to be using it all the time. Okay, the textbook has the version with complex numbers, and it has a much shorter proof that's like 4 lines long. But this is an equivalent fun way to do it. Okay, questions or comments about the proof of the Cauchy, Schwarz, Bujankowski inequality? Okay, let's keep going. So next up we have triangle inequality. So you might ask, is triangle inequality satisfied? So x plus y is less than the norm of x plus the norm of y. This is, in the textbook, this is corollary 3.2.10. So if you have an inner product and it satisfies the axioms of the inner product space, you'll notice nowhere on the list of the axioms did it say the norm has to satisfy the triangle inequality. As soon as you satisfy all the ones that give you Cauchy-Schwarz, you automatically satisfy this. And not only can I tell you that the norm of x plus y is less than this, in an inner product space, I can tell you exactly how much less. So in fact, the norm of x plus y, okay, I'll tell you how much less when you square it. Okay, well, you'll see in the proof. In fact, can say more. Can say more. I'll be cryptic. Let me be clickbaity. Find out with this one weird trick. Okay, what's the norm of x plus y squared is equal to the x plus y with x plus y. These you should get used to every time you see an inner product. Or every time you see a norm, you write it out as the inner product of the thing with itself, and then you can expand this out. So this is x plus yx plus xy plus yy, just like we did before. And that is equal to, in a real inner product space like we're doing here, this is x squared plus, and you get a plus y squared. And these two combine. This is twice xy in the real version. Okay. And so this says x plus y squared is the x squared plus y squared plus 2xy. And 2xy, okay, here's all I got to do is add an absolute value. And now I can do the Cauchy-Schwarz. So by Cauchy-Schwarz. You'll see dash CS means Cauchy-Schwarz. Should we include the B? I think we got to make a call. You guys want to include B everywhere? Who votes for let's be inclusive and include CSB? Who thinks just CS is fine? Okay, let's just do CS. Sorry, Mr. or Mrs. Boyankowski. I do not know who you are. Okay, x, y, plus y squared. Okay, and this thing you might recognize. This thing is exactly the norm of x plus the norm of y squared. Okay, so altogether, x plus y squared is less than x plus y all squared. And if you want to know exactly by how much more, it's by the difference is exactly the steps where we made an inequality. So the difference between x, y, if it's negative or positive, that will matter. And it's how much smaller is xy than the norm of x times the norm of y. That was the cosine. So if you want to know exactly how much larger xy is than x plus y, then all you got to do is figure out the cosine of the angle. So this depends on the cosine. Depends on the cosine. So in practice, you can often figure out how much larger x plus y is versus x plus y norm versus x norm plus y norm by looking at the angles. But in general, it's just true. Okay. And so altogether, what this proves is that the thing that I said right at the beginning, altogether we have justified the fact that an inner product space is a special type of normed vector space. So we have justified this big bubble living over here, right? Anytime you have an inner product space, you define the norm, it satisfies triangle inequality and all the other axioms, and it's definitely a normed vector space. Okay. Okay, there's something called parallelogram law. I'm not gonna go hard on parallelogram law. Maybe I'll tell you I'll give you the statement of parallel. Here, I'll copy directly from my notes here. You will appreciate the notes. Okay, parallelogram law says something about parallelograms. The length of a parallelogram satisfies this property that the length of x plus y squared plus the length of x minus y squared is the length of twice x squared plus y squared. And the proof is just expanded out. This is something you can do in inner product spaces. I believe it's true that every normed vector space that satisfies the parallelogram law must be an inner product space. I think that's the only reason to learn the parallelogram law. But the textbook doesn't do that. So I don't know. We're going to skip the parallelogram law. If you want to draw a little picture, it's called the parallelogram law because you can think of x and y as two sides of a parallelogram. And this is something about the two diagonals of the parallelogram compared to the four sides of the parallelogram. But we don't really need it. So let's just leave it at that. I guess I suppose I could at least make it a bit bigger for people who are copying. Okay. All right. What else can you do in an inner product space? Here's an actual extremely important definition that we will use all the time and will be a cornerstone of everything we're doing is the so-called orthogonal vectors. Two vectors are orthogonal when their inner product is 0. Let's do some examples. And the main example I'm going to give is the sine of nx and the sine of mx are orthogonal in L2 when n is not equal to m. So in other words, if you have oscillations at a frequency of n and you have oscillations at a frequency of m, those two things, they are orthogonal vectors in the L2 space, and specifically in L2 of minus pi to pi. This will be the sort of most important orthogonal sequence. So what this means is if you did this integral, this will be 0 if n is not equal to m. And what this is telling you is that the sine functions, they are orthogonal vectors. They're going to be sort of a different basis that you can work in. That's what Fourier series will be. Fourier series will say, write your vectors using these orthogonal vectors rather than the vectors that you were thinking of before. If n equals m, then of course it can't be 0 because you have the integral of sine squared. Does anyone know what the integral of sine squared is from minus pi to pi? Yeah.
0. No, that's wrong.
The integral of sine is 0. Yeah. But sine squared can't integrate to 0 because sine squared is positive. It's above 0. Let me draw a graph of the function. So,
It's pi, isn't it?
it's pi. Okay, very good. Okay, why is it pi? The sine squared function, it goes up and down between 0 and 1. So it looks like this. And it has an even number of, okay, I'm bad at drawing. You have to imagine that they're all equally spaced, okay? And it goes up and down between 0 and 1. And on average, its value is a half. This is the fact to remember, is that the average value is 1/2. The average is 1/2. Why is the average 1/2 and not 2/3 or something? Well, remember, sine has a buddy. Sine's buddy is cosine. And cosine also goes between 0 and 1 when you square it. So sine squared goes between 0 and 1. Cosine squared goes between 0 and 1. They both have the same average value. Sine squared and cosine basically look exactly the same. They bounce up and down and up and down. And they have an even number of bounces. They have the same average value. Why does that average value have to be a half? Yeah.
Because when you add them, it's 1.
When you add them, it's exactly 1. So not only are sine squared and cosine squared bouncing up and down, they bounce up and down in perfect lockstep. Okay, this picture is getting extremely exciting, so let's zoom in. Right? Cosine looks exactly the opposite. It looks like this. Right? Because sine squared plus cosine squared always has to be exactly 1. And so they have the same integral, and that integral has to be a half for both. Okay. This is an important example that we're going to have. So their average value is a half, so the integral will be pi, because the length of the bottom here is 2 pi. So on average, a half times 2 pi. Okay, this is a really important example. We're going to come to this later in the course. That's why I'm telling you now. Are there some other interesting examples of orthogonal vectors? Well, there's the usual in 2 dimensions perpendicular thing, right? But we did that already. Okay. Here is the reason we care, one of the reasons we care about orthogonal vectors. Ooh, okay. Is there a way for me to, okay, whatever. Oh, that's the whole page. We don't want the whole page. Here's an important theorem you might have heard of. The Pythagorean theorem. If x and y are orthogonal, then the norm of x plus y squared equals the norm of x squared plus the norm of y squared. Do you remember? I said earlier, what happens? The norm of x plus y squared is always less than the norm of x squared plus y squared. And then there are these inequalities that depend on the cosine of the angle. Well, when they're perpendicular, the cosine of the angle is 0. So the proof is going to be, you can do the proof from before, or let's just write it out again because I think it's instructive. So x plus y, you should get very good at expanding this out with FOIL or whatever method you do. And okay, this is the norm of x squared plus 2 times the xy plus the norm of y squared. And now this is equal, not a less than or equal to, since the norm of xy equals 0. This is equal to the norm of x squared plus the norm of y squared. And that's Pythagoras. So Pythagoras is like a snap in terms of the inner product. Much easier than the geometric proof the Greeks did. Okay. This one's really important. So for example, this will tell you what happens if I have a function and I want to do the L2 norm. So this is an example. What happens if I want to do the L2 norm of 2 times the sine of 3x plus 5 times the sine of 7x? Okay, so 2 times the sine of 3x plus 5 times the sine of 7x, some crazy weirdo function that goes up and down at frequency 3, but also at frequency 7, and they're added together. All right, we gotta. It's getting too hard to imagine. We need help. We're gonna get Desmos and really do it. Open the graphing calculator. Oh no, this is very embarrassing. I have so many tabs open, I can't find the tab we're on. Okay, nobody laugh at me. Okay. What did I say? 3 times the sine of 2x. 2 times the sine of 3x, probably? I think I did prime numbers in order. Okay. Plus 5 times the sine of 7x. So you thought my tabs were bad. Wait till you see this function. 7x. Okay, not equal, though. Plus. Okay, there you go. Okay, wiggly boy. It goes up and down, all over the place. Crazy looking function. But suppose somebody says, now integrate it. Oh my goodness gracious, they told us to integrate it. What are we going to do? Right, so they said find the L2 norm of this function, which is the integral of the thing squared. They said square it up and integrate that from minus pi to pi, please. Right? This is a headache. You got to square it, integrate it. Oh my goodness, it's going to take you forever. But by the Pythagorean theorem, it's actually quite simple. So first of all, the thing to notice is that this thing is orthogonal to this thing. So x, call this thing x, call this thing y. X is orthogonal to y. Orthogonal to y. The inner product of xy equals 0. Remember, that was the thing I said. If they have different frequencies, they are orthogonal. So therefore, by Pythagoras, this equals 2 times the norm of sine of 3x squared. Okay, we'll do the norm squared. Plus the norm of 5 times the sine of 7x squared. All right, this is already a beautiful simplification. We're doing it in L2. Okay. But not only that, I think we can get the exact answer on the board here. How do you simplify it further? So that was by orthogonality. You can split them up. You don't have to deal with sine and sine together. You do them individually. But you can even go further. What else can you simplify? Yeah.
Well, you can take out the 2 and like the coefficient.
Yeah, you can take out the 2. So the 2 becomes a 2 squared. And then you just have the sine of 3x in L2 squared. And then you can also take out the 5. So that becomes a 5 squared. And you have the sine of 7x in L2 squared. So that's one nice thing. That's scaling, right? Can we answer the actual integral? What is the norm of the sine of 3x? The norm of sine of 7x? Yeah.
0.
They're not 0. They're not 0. So again, this is the same mistake that was made in the back row, right? The integral of sine is 0, but we're doing the integral of sine squared. We're doing the integral of sine squared. So it's not 0, but it is another special number. Yeah. It's pi. Yeah, this is what we did before. It's 2 squared times pi plus 5 squared times pi. Also known as 2 squared plus 5 squared times pi. So look, we did the whole crazy integral of that weirdo, wacky function. This is part of the reason that Fourier series are so useful. You have Fourier series, super crazy function, but the Fourier series are orthogonal of each other, and all sorts of things you'd want to calculate, you sort of calculate them term by term, and the fact that it's a weird, crazy mix doesn't matter. The only thing that matters is the individual coefficients. So this is the kind of reason that orthogonal things are important, is you can use Pythagoras on them and calculate these kinds of things. And I'll say the norm of sine of nx squared in L2 equals pi by previous integral. Okay, beautiful. All right. Okay, Hilbert space. I think the next thing we get to is truly the mind-bending one. Okay, yeah, all right. Things are gonna heat up a little bit. So far it's been pretty tame, but now we're gonna see something a little weird and wacky. Who's ready? I know, hey, hold on, I have to ask who's not ready, so the lazy people will keep their hands down and then we'll plow forward. Who's not ready? Okay, good, everyone's ready, okay. Okay, here is a thing. In normed vector spaces, there was convergence in norm. So we said the limit as n goes to infinity of xn equals x. That means the xn minus x, the limit is 0. So this is convergence in norm. Convergence in norm. Right? This is what we saw in chapter 2, convergence in norm. We saw in chapter 1, right? This was the only type of convergence in chapter 1. In chapter 3, there is a new type of convergence. This type of convergence is called strong convergence. So this is AKA strong convergence. So when you hear someone say strong convergence, that's the ordinary convergence you've been doing the whole time. That thing, okay? This type of convergence still exists. Every inner product space has the norm, and this type of convergence is totally legit. You can talk about it. It's the regular convergence, also known as strong convergence. There is a new type of convergence on inner product spaces only. So, well, actually, okay, that's not true. It exists on other spaces as well, but it's different. Okay, in inner product spaces, there is another. It's like that scene in Star Wars. Maybe you guys are too young for that. There is another. Okay. Can anyone guess what the name of the other convergence is? Yeah. Weak convergence. Yes. Weak convergence. Weak convergence. The people who name these things really should be thrown in jail. Like, I remember I was studying for so when you do your PhD, there's this thing called the qualifying exam where you like have to know all of analysis, and they quiz you on the blackboard for an hour about analysis. And I was like studying this stuff, and I was like, okay, strong convergence, got it. Weak convergence, got it. And then I like kept reading, and there was like a vague convergence. And I like threw the book. Vague convergence, go away, guys, come on, we need a better name. Okay, anyway, you don't need to know vague convergence, but you do need to know weak convergence. Weak convergence. Here's how I think about weak convergence. In strong convergence, it's the norm. In weak convergence, it's sort of saying the inner product of the thing that you're doing the limit of will converge. So very vaguely, the idea is, so the xn's, they're not converging in norm. It's not that the xn minus x are converging in norm, but the inner product of xn minus x dot is converging to 0, goes to 0. I have to tell you what I mean by this. Okay. So in strong convergence, the norm of xn minus x goes to 0. In weak convergence, the inner product of the dot, what does that mean? What it means, for every, so this is the idea, and this is the actual definition, which is definition 3.3.10 in the book, which says, for every fixed y in your space, we're denoting the space as E, the inner product of xn minus x with y, that inner product converges to 0. The limit as n goes to infinity of this equals 0. So in other words, for every fixed possible input into the inner product, the limit is 0. And you should compare that with strong convergence, where there is no input, right? It's just literally the norm of xn minus x has to converge to 0. That is weak convergence. The first kind of proof you would want, and this kind of justifies the name a little bit, 3.3.11, which is that strong implies weak. If you converge strongly, then you converge weakly. Oh, by the way, the textbook writes a notation. I'll write this notation for you. Xn converges to x with a W means weak convergence. So watch out for the W's. Okay, but strong implies weak. So proof. Suppose xn goes to x strongly. Let's say i.e. the norm of xn minus x is converging to 0. Then for any y, the inner product of xn minus x with y, you can write it by Cauchy-Schwarz. It is less than the norm of xn minus x times the norm of y by Cauchy-Schwarz. Right? So you give me y, I do the inner product of the thing, my difference with y, and that is less than just the norm of me times the norm of you. And that's going to 0. This goes to 0 since xn minus x goes to 0 and y is fixed. Right? So because you can't change your y halfway, y is some constant number. This is something going to 0 times a constant that goes to 0. Okay, so that's strong implies weak. So that kind of makes sense. There's some more crazy theorems about strong and weak convergence, but I want to give you some examples now, because otherwise you can't understand what this kind of thing is. So that's what I'm going to do now. Examples. And this will harken back to our chapter 1 days. Let's look in the little space L2, which is sequences with the norm of, okay, I'll write the inner product actually. The inner product of A and B is the infinite sum of AI times BI, right? That's the space little L2. I'm going to make a sequence. Here is my, again, don't get confused, right? The space is sequences. So I'm now going to have a sequence of sequences. So I'm going to make a sequence called En. Let En, it's a sequence, be a sequence in L2, i.e. each En is a sequence. Each En is a sequence. So it's a sequence of sequences. Okay, I'm going to tell you what they are. E1 is the sequence 1, 0, 0, 0, dot, dot, dot. It's all ones. I suppose I should write it like this, with because order matters. E2 is the sequence 0, 1, 0, 0, dot, 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 dot. E3 is the sequence 0, 0, 1, 0, dot, dot, dot. We had this sequence of sequences in chapter 1. Maybe you remember from studying from the midterm. My pen is going insane. Okay. This is a sequence of sequences, and the rule is that En equals of I equals 1 if I equals n and 0 otherwise. So it has exactly 1, 1 in the nth component, and it has all zeros everywhere else. The sequence En. You might remember that the norm of En is always 1. The norm of En, it's the sum of the squares of the entries. And En has exactly 1, 1 and all zeros. So this infinite sum, it is infinitely many zeros. And then there's 1, 1 that you add up. And so it's always 1. Always 1. So En is always norm 1. It's definitely not converging to 0 strongly. So En does not go to 0 strongly in norm. Right? Because if it did go to 0 in norm, then the norm of En would have to converge to 0, and it's not. The norm of En is always 1. You might remember from chapter 1, we said that En goes to 0 pointwise. Pointwise. And that's because if you evaluate it at every single point, it's eventually 0. Then the statement we are adding to the soup today, fact, claim, fact. En goes to 0 weakly, i.e. En converges the limit as n goes to infinity of En equals the 0 vector weakly. Weakly. Okay, let's prove it. Proof. So, again, weak convergence is this idea. You have a test thing, and you test your function, the thing you're trying to prove convergence on, against the thing you're given, right? It's a for all y, right? That's the definition of weak convergence. You have this, someone gives you a y, and you say, I do the inner product against your y, and I make sure that the limit is what I want. Okay, so we have to be given a y. Let y in L2 be given. Well, L2 is a sequence space, so you just gave me a sequence of things, and now I'm going to do the inner product of En, okay, En minus 0, but En minus 0 with y. And this is the infinite sum from I equals 1 to infinity of En of I times y of I. Can anyone simplify this infinite sum for me to make it something a lot easier? Yeah.
The sum of all the terms of y.
Well, I mean, the sum of all the terms of y is I equals 1 to infinity of yi. We have that already. But you want to say less than or equal to? that what you're trying to say?
Yes.
Okay, I don't want a less than, I want an equals. Yes?
Y of n.
It's y of n, exactly, very good. Yes, it's y of n. And the reason it's y of n is because ei is almost all zeros. Most of the terms are 0, except for when I equals n, then it's 1, and you have 1 times yn. Okay, so it's yn. Okay, we want to prove that this goes to 0. We would like to show this goes to 0. Why does this go to 0? I shouldn't have called it y, because now, okay. Why does y go to 0? Why does y of n go to 0? That's what we need to show. What do we know about y? We only know one fact about y. Yeah.
As n goes to infinity, those elements at the end of y have to be getting smaller and smaller and smaller.
That's what we're trying to show.
The condition of L2.
It's the condition of L2. Very good. So the reason theyn's have to go to 0 is because yn is not just any sequence under the sun. Yn is a sequence from L2. And L2 has a condition that means that the elements have to go to, the terms have to go to 0. Very good. So because y is in L2, and therefore the infinite sum from I equals 1 to infinity of yi squared, that is a finite number. And if you have a sum that is finite, all the individual terms have to go to 0. Be careful, the reverse is not true, right? If the individual terms go to 0, the sum could still be infinite. But if the sum is finite, then definitely for sure, the limit of the terms is 0. The limit as n goes to infinity, and I guess it's really the limit of yn squared is equal to 0. And if the limit of yn squared is 0, then the limit of the y's is also 0. Okay, and that's the proof. So en picks out the nth component of y, and that goes to 0 because the space L2 is square summable things, and their terms have to go to 0. So very nice. So the ENs go to 0 weakly, but not strongly. And you might have had some experience studying the ENs before. This is exactly what we're trying to say. When we say something goes to 0 weakly, we're trying to capture this idea of it kind of goes to 0, but like the problem is just like moving away, away, away. I'll give you one more example. And this is an example in L, again, our favorite space, L2 of minus pi to pi, where the Fourier series will live, okay? And the function sine of nx, so call that fn of x. That's a function that's in L2 of minus pi to pi. Fact, claim, whatever you want to call it, fn goes to 0 weakly. Goes to 0 weakly, not it goes to weak 0, okay, weakly. So 0, by 0 I mean the 0 function. The function that's always 0 in L2. Once again, this is kind of a weird statement. Let's open, this is a good one for Desmos. All right, if we do the sine of nx, and I have to add a slider for n. Okay, and let's also, do I want to restrict myself between 0 minus pi and pi? Minus pi less than x less than pi, then your sine, and then, yeah, okay, that's great. Okay, so there's our function. Let's zoom in a bit. So this is the function, but the exciting thing is I can animate it as we make n bigger and bigger, because the statement is about something that happens when n gets bigger and bigger. So what happens to this thing? It looks like that. Okay, now it's getting smaller. Okay, 300 was ambitious. Let's try 30. Okay. I guess let's always have it increasing. So you add more and more layers to this thing. And we're saying that this is converging to 0. Of course, it doesn't converge. This one does not converge pointwise, right? If you're at some point on the x-axis, you see an infinite sequence of 1s and 0s and negative 1s pass by you as n gets bigger and bigger. It's not converging pointwise. It's not converging in norm. The norm of this thing, again, is always pi, right? Or square root of pi. The norm squared is always pi. That's what we proved. But it is converging to 0 weakly. And what this means is if you integrate it against some other function, let's take some other function. Let's take the function y equals x. Okay, that's a beautiful function. So what happens if you integrate the red function times the green function? Well, okay, at first, that's going to be, a nice integral. No problem, that's going to be some positive integral. But what happens as n gets bigger and bigger and bigger? What can you say about this integral? If you multiply the green function times the red function, I claim it's going to be a really small number. Why will it be a really small number? Yeah.
Because as n gets bigger and bigger, the fn spends like more time being 0 because it's intersecting 0 more times.
Oh yeah, okay, that's a very interesting thing. Yeah. So you're noticing that it's touching 0 a lot. And it's true it's touching 0 more times, but it still touches 0 only a 0% chance. So the fact that if you look only where it's equal to 0, that's not enough to conclude we'll go. That's a very good idea. But it's not about how often it spends at 0, it's about how quickly it goes between zeros. So it's not literally equal to 0, but it's how fast are we switching. To make this a little bit more precise, it's switching between positive and negative on very short intervals. So it's going positive, negative, positive, negative, positive, negative. So when you integrate it, you're going to integrate some part of the function where it's positive, and then you're going to integrate it again where it's negative, and those are going to cancel out. So the integral is going to go plus minus, plus minus, plus minus, plus minus, and as this thing shrinks, as the distance between them gets smaller and smaller, then the function, the green function, is not changing much on those intervals. So the positives and the negatives will almost exactly cancel out. So that is the reason. I will tell you, I was thinking, I won't put it on the midterm, but I was thinking about putting this on the midterm. So it is the kind of thing you can prove with the stuff we've been doing. So this could be a good exercise as you're studying for the midterm. Here is the proof. I won't do the proof, but I'll tell you the proof has two parts. Proof. First, step one. Prove that for step functions, only step functions, the integral of fn of x times the step function, let's call that s of x. So s of x, will s for step function dx. From minus pi to pi, this converges to 0. And for step functions, you can actually figure out the integral. Not only is it converging to 0, it's 1 over n times something equals 1 over n times stuff. And that goes to 0. So for step functions, if the test function that you're testing fn with is a step function, the theorem is true, right? Because weak convergence means that for any given test function, the inner product is going to 0. For step functions, it's true. That's not hard. This is like some actual integral. You really do the fundamental theorem of calculus. You really figure out what the integral is. It's got a 1 over n. It's something nice. Step two. Use the theory of Lebesgue integration from chapter 2 theory, to show that if f is in L1, say, L1, and use step 1. So step 1 says check it for step functions. Step 2 says for a Lebesgue integrable function, use step 1 to prove it for f. To prove the inner product of fn f, which is the integral of the product fn of x times f of x goes to 0. And this step 2 was the thing I was thinking about putting on the midterm. This is a pretty good example question. I won't actually put it on the midterm, but it's good practice nonetheless. Okay, I'm a few minutes over. Thank you for waiting. I'll be around for questions or comments or anything else. And I have extra office hours on Monday. Everything is posted on the course link. There's like a midterm 2 info. So check that out. It's got some problems as well. And good luck studying. And we'll see everybody on Tuesday for the midterm.